can you see my screen, everyone?
Yes, yes.
Okay. And Vaishak, recording has started, right?
Yeah, it started.
Okay. Okay, so thank you everyone for joining. Okay. So today what we are going to do is I will show how to use the models which are available from RTDL, and maybe just we can go through the RTDL paper first, and let me just open that. Yeah. Okay. Just yeah. So you can see the paper, right?
Yeah, yeah.
Yes, sir.
Okay, fine. Yeah. Okay. Okay. So this paper is called Revisiting Pre-training Objectives for Tabular Deep Learning, and this is from this Russian group. Now, Yandex, as a lot of you might be knowing, is the search engine in Russia. And just a second. Okay, so there is this university, National Research University, Higher School of Economics in Russia again. So these guys, Yuri and others, they have been they have been working a lot on tabular datasets for Kaggle for different competitive competitions, data science competitions, and so they have kind of summarized their knowledge of whatever they have learned over the past maybe 10 years in this paper. So this paper is really concise and contains a lot of information on how you would approach tabular problems using deep learning. Okay. Now, this paper is actually a follow paper of, I'll just show that first. So they published this first paper in Neuro IPS in 2021. It is called Revisiting Deep Learning Models for Tabular Data. Okay. And in this paper, what they say is that there are so many different models for tabular datasets, and people use XGBoost, Light GPM, CatBoost, gradient boosted decision trees, different multilinear perceptrons, different models. But they are trying to generalize. So maybe we can go through the abstract. They say that the existing literature on deep learning for tabular data proposes a wide range of novel architectures and reports competitive results on various datasets. However, the proposed models are usually not properly compared to each other, and existing works often use different benchmarks and experiment protocols. As a result, it is unclear for both researchers and practitioners. So, here I am, and we are basically practitioners. We are not developing these models, right? So, it's unclear for both what models perform best. So, that is a big problem that everybody has. And additionally, the field still lacks effective baselines, that is, easy to use models that provide competitive performance across different platforms. Problems. In this work, we perform an overview of the main families of deep learning architectures for tabular data and raise the bar of baselines in tabular DL by identifying two simple and powerful deep architectures. So the first one that they identify, so they develop, is called the ResNet architecture. ResNet is used in computer vision and in other deep learning tasks, And the other one, so they say, is the gradient boosted decision trees. But they conclude by saying that there is still no universally superior solution. Okay, so what they do in this paper is that also they introduce the transformers for tabular data. So what they do is, see, there are these data sets, right? California housing prices, the okay, so California housing is called CA, adult income is AD, Helena, and then there are these other data sets. So different data sets have different types of problems. For example, they so mm, primarily wherever you see RMSE, these are all regression problems. Okay, and where you see accuracy, these are all classification problems. So California housing uh, data set, the task is to basically predict the price of a house given different features like area or location, or uh, there are different predictors. But these are all tabular data sets. So what they want is to develop a general purpose algorithm, or to have a framework in from where you can, like, you can say that you have done a comprehensive set of experiments and you don't need to do anything further. So what they found out is, like, for example, for California housing dataset, FT transformer was performing good. FT transformer in fact was performing good for a lot of cases, and you can see the average rank of FT transformer is the best in this case. um, okay, so, and but still you can see that for AD, this GrowNet is GrowNet, Auto INT, these are also performing good. And for this YE dataset, Node is best. Node is even good for these two datasets. Okay, so they what they do is they don't just run these models, they also perform hyperparameter optimization. So they give for different data sets. So these are the different data sets. What is the train validation that they do, how much of the samples are in training and validation, and what is the batch size that they use. And you can see this big table. Okay, so these are the uncertainties as well that they have computed, and they provide the options for hyperparameter tuning as well. For example, for the FT transformer hyperparameter space, you can see that uh, they use the in Optina they use the parameters as the number of layers should be from 1 to 4. The feature embedding size should be uniform from picked from a uniform distribution from 64 to 512 residual dropout. So there is different hyperparameters of FT transformer than for ResNet, for MLP, for GrowNet, for Cat Boost. So this is what they did. Now this paper is called RTDL. So RTDL stands for Revisiting Tabular Deep Learning. Okay. Now the follow-up paper was this one. Okay. So this paper, the follow-up one, also came out, I think, in a very good journal. Or okay, this one also, I think, revisiting pre-training objectives for tabular deep learning. They have. I think this one also got published in NIPS 2022. And so in this paper, what they are doing is they are saying that embedding the data sets, whatever the predictors you have, using some kind of embedding to it. Now, what I mean by embedding is, okay, so just give me a moment. They have some, no, actually, this is even one step further. We are doing embeddings. Yeah, Vaishak, I think we need to see this paper as well, right? This is looks even.
Yeah, embedding one.
Yeah, we need to see the embedding one, but the I'm saying the other one, it looks even more advanced. Anyways,
Yeah.
um, so what we will basically see the embedding paper first. Yeah. So, okay. So they say that on embeddings for numerical features in tabular deep learning, and what they do here is that they embed the predictors or the inputs with different functions or okay. So they have, yeah, these are the embeddings that they have. Okay, so you can see this, right? Name embedding function L is linear, LR is ReLU into linear, LR is ReLU linear, ReLU linear. Q is PLEQ. So PLE is a function. You can see they define that PLE function. Okay, anyways. So PLE is Q, and then if you do a linear into PLE, it's becomes QL. Then ReLU linear PLE becomes QLR, then QLR, and then PLET, and then you have the periodic. So periodic, I think, is some kind of sign. So you are just kind of uh, applying some functions to the data set, the input data set, the predictors, and that is something that you are then inputting into the model. So what they find out is that even a simple model like MLP, okay, it performs as good as transformers if you use a reasonable embedding to it. For example, you see this, okay. So you see this one, MLP QLR, okay. For this data GE, you can see it's giving the metric as 0.646, and which is going similar to like what transformer models are giving. Is MLPQ is giving up to 0.653, and transformer, just a simple transformer is giving 0.632. So a multi-layer perceptron model can beat a transformer, but the condition is that you need to provide good embeddings. So there are so many options for embeddings as well that they have provided. Okay, so for example, you see this, and also in this, so they also compare with Cat Boost and XGBoost, which are the standard state of the art, like in any kind of tabular problems. But you can see that the deep learning models, they are outperforming XGBoost, for example, for the California housing prices dataset. You can see, I think this is the RMSE. So XGBoost is giving 0.434 and Cat Boost is giving 0.430. Whereas Transformer TLR, you can see we are getting 0.423. Okay. So this is the RMSE which we are getting from Transformer TLR. And Transformer TLR basically means the TLR embedding with Transformer. So this is what we are trying to do for different projects. For as I can see, like different people are there in this call. So for different works, the different for example, for Sonica's work, for Cloudburst, or for Prantic crop yield forecasts, or so these embedding models, they are they are very important. Now I'll just show you what we have. So we have developed like a Docker container of this embedding RTDL. Okay. So you can just go to this satellite bathymetry. Yeah, even for the bathymetry, if Om is here for the bathymetry project, uh, so you can just uh, you can go to the tags and then do a Docker pull. Okay, so you just need to do Docker pull and then this Docker repository in satellite bathymetry. This is the tag rtdl embed underscore v1, right, Vaishak? Hello.
Yes, yes, yes. Yeah, that's the one.
Yeah. So then what you need to do is you just go to the Apollo server. Okay, and okay, let's say we check. Okay, so right now all the GPUs are available. So then you say, okay, so you just pull it first, and then once you pull it, you will get this one here. Okay, so then you just give Docker run it minus GPUs all, and then the name of the repository. Okay, so you can see now we are we are inside the container. Okay, you can see, right, everyone?
Yes, yes.
Okay, so now you can just go and check the environment here. So we have already created num embeddings. So just to source activate num embeddings. Okay, and this is a CUDA container. So your NVIDIA SMI will work here. Okay, so just go to tabular DL num embeddings, and then we have created a set env.sh. Okay, so just source set env.sh. Okay, now just go to the GitHub page of this embedding. Okay, and so we will just download the data from here. So we are not put the data in the container, that was getting too huge. So just download the data, do a wget. Let's wait for some time. Are there any questions? Are there any questions? Am I audible? Hello.
Yes, you are audible.
Okay. Okay, so the data is downloaded. You just do a tar minus xvf num embedding over this. Okay, so now you can see that we have the data folder here. So just follow what they have provided. Okay, so we have already done this. Okay, let's just do export CUDA visible devices. Okay, so I'll just check if this has been assigned. Yeah, and then what you do is, okay, yeah, for example, if you want to run MLP, okay, so just copy this command. What this will do is, okay, just I'll explain about it. So you can see that there is an exp folder. In the exp folder, you can see that there are these all different models. Okay, now if we go into a particular model, let's say the MLP, you can see that there are the different data sets. Now for corresponding to each data set, there are 2ml files, .2ml, as well as folders with the similar names, right? So what you have to do is, so these 2ml files are the configuration files that are required. Okay, so you can see this. So here, for example, this is 0, and it uses the program bin train 0.py. Number of trials in Optina is 100. Okay, and then the data is data California. Okay, so you can see that we downloaded the data. Okay, and inside data you have these different data sets. If you see California housing prices data set, so it has got X num test, X num train, X num val. So these are the train, test, and validation data sets. Okay, and then you have the IDX test, IDX train, IDX val. The info.json consists of the, I'll just show that, or I'll just go into the data. Okay, so if I just do Python import numpy as np, okay, and np.load x num test.npy, So you can see that this is your test data. If you see the shape, it has 4182 rows and 8 columns. So basically 8 predictors, and the number of rows are 4128. Now, if you read the Y test, let's say corresponding will be Y test, which is the housing prices. Now you see it's got these are the housing prices, and if you see this has got the shape 4128. Okay, and then let us also try for IDX test. Vishak, what was this IDX test? I
No,
actually
IDX files are not needed actually.
we don't need this, right? Yeah.
No, we don't want.
Okay, so these are not required, and you can see info.json. So you can see the name is California Housing, ID, task type, regression, number of numerical features, number of categorical features, what is the train size, val size, and test size. Now, why I'm showing you all of this is because you will be going back and making your own xnum test, xnum train, xnum val, y test, y train, y val, and info.json corresponding to your datasets. And you will be modifying info.json and other files you will be just making for your tabular data. So I will just show you how to run the California housing prices dataset, and then you can just implement that on your own tabular datasets. So what you have to do is you just so inside exp stands for experiment, exp mlp California zero tuning dot to ml. So you just so what you just do is so if you use a particular configuration file, it will create a folder in that place which will be similar to that file. Okay. So what we will do is we will copy the zero tuning.ml to, let's say we call it two tuning.ml. Okay. And then so we have now created this one two tuning.ml. Okay. So then what you do is you just run this bin tune.py and the give the 2ml file as the argument. They have the one to tuning.ml will give us two tuning.ml. So now you see that the yeah the training has started, and we'll see if the GPU is being used. So you can see that the first GPU is being used. Okay, around 2 GB of 39.59 GB GPU RAM is getting used. So after you do this, it will create a folder to underscore tuning in this path. Okay, exp mlp California. After that, what you do is so you if you remember we were training with one seed. Seed is basically when you initialize the weights. If you change the seed, then whatever Xavier random initialization is being done initially that changes. So they are also training with 15 seeds, and they create uh, 15 different models, and then they basically combine those models, create ensembles. So they create three ensembles of five each. Okay? So this running this Python bin ensemble exp California and giving the folder of the ensemble name. So what this will give you is eventually you will get the predictions.npz file. You will get the predictions.npz file in the same path, and that prediction.npz file, if you just load use numpy.load, and then it's a basically a dictionary. So you can just and the dictionary has the keys which are train test val. If you just load that dictionary, it will give you the values. Now from those predictions, you just what I'll do is I will
Try
one
to give like epoch trials as 10 or 5, like so that.
and like do okay. Yeah, so EXP P California. Okay, so let's say we give the number of trials as 1. Okay, so then we do Python bintune.py xpmlb California 3.3 underscore tuning dot to ml. Okay, it's done. So you can see in exp mlp California, you can see there is a new folder 3 underscore tuning, which consists of 4 things: checkpoint, raw config.json, report.json. You can just open report.json and it will give you the details of this run and the best metrics as well. So you can see that it's giving you the details of the GPU, what is the data, what are the best hyperparameters that they have used, the file. Then you can see that they also provide the RMSE for train, validation, and test. Right. So after that, after training, if you do create 15 different ensembles, no, not with one tuning, with so you just have to give Python bin evaluate.py exp mlp California, and we are having 3 tuning, and then you're giving the number 15. So that basically means 15 different ensembles.
Excuse me, sir.
Yeah. Who's this?
I have a question.
Hmm. Yeah, please go ahead.
What is the meaning of this ensemble technique?
What is the meaning of ensemble technique?
Yeah, this ensemble. Yeah, this is encode it is taking 15 different encodings and then combining these models,
Seeds.
or what is
No,
doing
no,
it
no, no.
is.
15 different seeds. See, you ran the model first for different number of trials. So it gave you a particular set of hyperparameters. Okay. Now with those hyperparameters, you run for different seeds. Okay. And you generate different ensembles. Okay. Uh, Basically, and then you combine those ensembles. So using ensemble.py, and you run those ensembles using generate using evaluate.py. Is that clear?
Yes, sir.
Okay. Yeah. Who was this? I am not able to recognize.
Vishnu.
Oh, okay. Okay. So you can see that in EXP, MLP, California. So we have this 3 underscore evaluation. Okay. Why we have 3 underscore evaluation is because we ran 3 underscore tuning. Okay. So that is the reason we have 3 underscore evaluation. And what you do is you just say python bin ensemble.py and then run this ensemble.py over 3 underscore evaluation. Okay. This will generate, like for those 15 ensembles, it will generate ensemble mean of, or merge those 5 each and then give you these scores 0.493, 0.494, 0.490. Okay. So then what you can do is you can just go to EXP, MLP, California. Okay. So you can see 3 ensemble. Okay. You can see 3 ensemble 5, 0, 1 and 2 are the 3 ensembles. Okay. So here you can see predictions.npg file. Now you just go to any one of them. So you do import numpy as np, np.load predictions.npc. Then if you see this DZDS, this is a NPZ file. If you just say train, okay. So this is a prediction over train, okay. So you can see this 13209. You can do a DS test, okay. So this is a NumPy file, NumPy data array, and for the val. So what you do is just save these as CSV files, these predictions, bring them out, computer metrics. Okay. And for different models, you compute the metrics and develop a table like they have developed here. Okay. You see this table. See, like this. Okay. So here you have the different models. Let's say here you have the different embeddings. You will have only one data, right? So you make the table in such a way that you have MLP, ResNet, transformer, and then on columns you have the different embeddings and just fill the RMSE values. Also, in addition to this RTTL embedding, you also do your own CAT boost, light GBM, and XGBoost. That should be sufficient for like modeling the dataset. I mean, if you want to apply this to any competition as well, this is like comprehensive of whatever you can do. So that was all about RTDL embedding. And if you have any questions, just let me know. My suggestion is that I just stop the recording first.